Good evening, everyone. Welcome to Week 11 tutorial of Applied Thermodynamics course. I am Tananga Sutia, and we'll wait for a couple of minutes for others to join. And in the meanwhile, I will be sharing my screen. Okay, I hope you can see the screen. So we'll wait for 1 or 2 minutes. Okay, hello everyone. Today basically it's the 11th tutorial, and in this class we will be basically dealing problems that are related to psychrometry. Okay, so before solving the problems, let us have a quick look at the different basics of psychrometry that we will be requiring to solve the problems that are related to psychrometry. So first of all, let us try to understand what psychrometry is. Okay. It is the study of systems involving dry air and water, basically in the vapor state. Okay, in the vapor state, water vapor, and okay, so that means previously what we were dealing with, whatever air we were taking into consideration was the dry air, but here we will also consider the properties of the moisture. Okay, so that means if moisture is present, if the air is not completely dry, what are the different types of changes, how will be the change in the governing equations of the different mechanical devices like steam turbine or cooling tower or whatever may be the mechanical device. So what will be the changes in the calculations or working formula, this will be dealt in great details if moisture content is also taken into consideration along with the dry air. Okay, so that means now we will be basically dealing with the properties of the moisture. So for that we need to understand what is a moisture, okay, or basically we need to understand like what are the governing equations. Okay, so basically moisture, it refers to a mixture of dry air and water vapor, in which dry air is treated as pure component. Okay, so why dry air is treated as pure component? Because that means that your mass of the dry air will remain the same. Okay, the composition of the dry air will remain the same. Okay, so just let me draw. Suppose this is a container. Okay, and it contains dry air plus water vapor. Okay, so it contains dry air and water vapor. So for dry air, let me say that the number of moles is Na and mass of the dry air is Ma, and let me say that for the moisture, that is the water vapor, it is Nv and Mv. Okay, so now for this total mixture we can take it as N and M. Okay, so we can write the equation of state as a whole. Equation of state will be P equal to N R bar T by V. Okay, we know this. Now this we can write as M times R bar by M into T by V. Okay, now from Dalton's law, what we can write, that the total pressure P is nothing but the partial pressure of the individual gases. Now there are two gases present, one is dry air and one is moisture. So therefore the total pressure P can be resolved into PA and PV. Okay, and now this PA, I can write this one as YA into P, and PV, I can write this as YV into P, where YA and YV are the volume fraction of dry and moist air respectively. Okay, so this is the volume fraction. So that's why now our equation can be written for dry air as PA is equals to Na times R bar T by V, and that can also be written as M times R bar by capital Ma into T by V. Okay, and PV can be written as NV R bar T by V, and that is can be written as M times R bar by capital MV divided by V into T. Okay, so this will be MA and MP. Okay, so then we should also know another parameter, that is what is a saturated air. Now we all remember the salt solution, the sugar solution. When we can say that the sugar solution is saturated, suppose there is a glass of sugar. Okay, suppose this is a glass of water. Okay, this is a glass of water, and now you are adding sugar. Now you add sugar and stir with spoon. Now what it will happen, this will result in dissolution, or sugar dissolves. Yes or no? Now if you go on continuing this process, continuation of this process will lead to a point after which no more sugar gets dissolved, then we call this as saturated solution. Yes or no? In a similar way, we all know that a moist air is a mixture of dry air plus water vapor. Okay, now if you keep on go on adding water vapor, okay, a state will come when no more water vapor can be added. Okay, no more water vapor can be added. Water vapor can be added, and this we will call it as saturated moist air. Okay, now this we can achieve in by different ways, and that we will understand how we can achieve saturation. Okay, how we can achieve the saturation pressure or saturation temperature by as we go on after this. Okay, so yeah, so this is the one we will be basically have to understand like what is a saturated air. Okay, so now after this we will be need to know properties of psychrometry. Okay, so we should know some properties of psychrometry. So the first property is humidity ratio. Okay, so what is humidity ratio? It is the ratio of mass of water vapor to the mass of dry air. Okay, and it is also known as specific humidity. Okay, so humidity ratio, another name we also know this as specific humidity. Okay, so that means what? We denote humidity ratio by omega. Omega is nothing but mass of the water vapor divided by mass of the dry air. Okay, now from our ideal gas equation, I can write mass of the water vapor as mv pv into mv pv into v divided by r bar times t, and this one also I can write as ma pa into v divided by r bar times t. Yes or no? Now this means I can write this one as mv into pv divided by ma into pa. Okay, now what is mv? Mv is basically the mass of water vapor, and we all know that the mass of water vapor is 18.016. Okay, and the mass of dry air is 28.96. Okay, and this will be PV divided by, can I write this one as total pressure P minus PV from the Dalton's law partial pressure. So from here W is actually 0.622 times PV upon P minus PV. Okay, so this is basically the expression that we will be using for evaluating specific humidity. Okay, and its unit is kg per kg of dry air, or gram per kg, depends on who you express this one, but this is the standard that is your SI unit, I can say. Okay, your SI unit is kg per kg of dry air. So whatever we will be dealing with this particular chapter is all about per kg of dry air. Okay, so this is your humidity ratio, that is nothing but the mass of water vapor to the mass of dry air, okay, in the given sample of the moisture. Okay, next is relative humidity. Okay, and this we express this one as phi. Okay, so relative humidity, it is the ratio of mole fraction of water vapor in a given moist air sample to the mole fraction in a saturated moist air sample at same mixture temperature and pressure. Okay, this means what? That suppose this is a given sample. Okay, suppose this is my given sample and it is not saturated. Okay, and it is not saturated. Okay, and it is at a certain temperature and pressure P. Okay, now if it is not saturated, okay, then it will have a certain mole fraction. Yes or no? It will have a certain mole fraction. Say this is YV. Okay, that mole fraction of the vapor. Okay, mole fraction of the vapor, YV, mole fraction of vapor. Now if this would have been saturated at the same temperature and pressure, if this would have been saturated at same T and P, then mole fraction of vapor would have been what? YVS. S stands for saturation. Yes or no? So therefore my phi will be the ratio of YV divided by Y of VS. Okay, so this is your expression. Now we know that in question mostly all those properties are given which are easy to measure. Now mole fraction is not very easy to measure, so in question you will be mostly provided with the pressure values. That's why we know that the mole fraction and pressure has a relation that if PV is equal to YV times total pressure P, and PVS is nothing but YVS times total pressure P. Okay, so therefore my mole fraction phi now becomes PV upon PVS. Okay, so this is the expression which we will be mostly using for relative humidity. Okay, and unlike specific humidity, it has no unit because above it is pressure and below it is pressure, so it is basically a percentage of, that means what percentage of the vapor would have been present if it would have been saturated. Okay, so it gives a measure of how much vapor it can hold basically. Okay, how much water vapor it can hold, basically this gives us that measure. Okay, the next parameter or the property we need to know is the degree of saturation. Okay, so what is the degree of saturation? The ratio of actual specific humidity to the specific humidity of saturated at mixture temperature is known as degree of saturation. Okay, now that means what? In the previous case it was the ratio of the mole fraction, now it is the ratio of specific humidity, which we have already studied. Okay, specific humidity, so that means if degree of saturation is expressed as mu, this will be W divided by Ws. Okay, now we have already got the expression for W as 0.622 times PV upon P minus PV. Okay, so that means Ws will be nothing but 0.622 times PVS by P minus PVS. Okay, so we cut this, then what we will get basically PV by PVS times P minus PVS divided by P minus PV. Okay, so this is your degree of saturation. So that means we can write one more thing, mu is nothing but 5 times P minus PVS divided by P minus PV. Okay, fine. So this is the expression which we will be using to calculate the degree of saturation. Okay, and just like your relative humidity, it has no units. Okay, it is mostly expressed in terms of percentage. Okay, now let us say we want to calculate the enthalpy enthalpy of moisture. Okay, so how will we can calculate the enthalpy of moisture? So capital H, that will be HA, enthalpy of dry air plus enthalpy of moisture. Okay, so this is enthalpy of dry air plus enthalpy of moisture. Now what I can write this one as MA into HA plus MV into HB. So we know that everything we express in terms of per unit mass of dry air. Per unit mass of dry air, this expression will become H divided by MA will be nothing but HA plus MV by MA times HB. Okay, so that means this H will be nothing but HA plus W times HB. Okay, so this is your enthalpy of moisture, and its unit will be kilojoule per kg of dry air. You have to remember this thing. Okay, this is per kg of dry air. Okay, similarly we can also write an expression for U. Okay, so that will be nothing but U is equals to UA times W into UV. Okay, and this will be also internal energy of moisture, internal energy of moisture per kg of dry air. Okay, fine. Similarly we can also write an expression for entropy. Okay, so that small s will be equal to SA plus W times SV. Okay, now if the two different points are the saturation point, we will be dealing those parts in the later part. Okay, so basically right now we will remember this thing only. Okay, so this is also entropy of moisture entropy of moist air per kg of dry air. Okay, now comes the important part, where we will be dealing with different types of temperatures. Okay, so first temperature is the dry bulb temperature or we can write in short form this as dbt. Okay, so it is nothing but the temperature of a sample of moist air as measured by thermometer. Okay, so that means just you take a simple thermometer and you measure the temperature of the moisture. That particular temperature is nothing but your dry bulb temperature. Now if I will say that the temperature of my current place is say 20 degrees Celsius, okay, the air at this room is 20 degrees Celsius, I can also say that the dry bulb temperature of this room is 20 degrees Celsius. Okay, nothing more than that. Okay, next is what? Dew point temperature. Okay, or in short we can write this as dpt. Okay, so what is a dew point temperature? If we cool a sample of moist air isobarically, comma, the temperature at which condensation starts is called dew point temperature. Okay, or dpt. That means what? Suppose this is a sample of moisture. This is a sample of moisture. Now if you cool it isobarically at constant P, okay, so what it will happen? If you cool it constantly at constant pressure, that means you are removing heat from it, and that's why after a certain point of time what will happen? The that mixture of moisture will become saturated. Yes or no? After that it can no longer hold, because at a particular temperature, at a particular pressure, the saturation temperature is fixed. Yes or no? So after that, suppose it is a moisture and you are not looking any form of condensed water, that means what? The water is in the form of water vapor. Okay, so that means that water vapor it can hold now. Now suppose if you are reducing its temperature, so you are cooling it down, and we know that if we cool down vapor, it has a tendency to form condensed liquid water. Yes or no? So now you are cooling it at constant pressure, and suddenly at a particular temperature you will get dew form, or what you can say that condensed water droplets form. That particular temperature is called the dew point temperature for that particular pressure. Okay, so constant pressure until condensation happens. Okay, and this is basically you call dew point temperature. Okay, so now we have understood these two temperatures. Now there is third temperature, that is called adiabatic saturation temperature. Adiabatic saturation temperature, or sometimes it is called wet bulb temperature. Okay, adiabatic saturation temperature, or we can say this as wet bulb temperature, and that is called WBT. Now here what we do, see, in this forming of dew point temperature we just reduce temperature. Okay, we do not do anything with the moisture content, but here what we do, suppose this is a sample of moisture. Okay, suppose this is a sample of moisture. Okay, now you will keep on adding moisture to it. Now if you add moisture to it, at a particular time what it will, and this entire process will take place adiabatically. Okay, so after a particular time what happen, the amount of water vapor it cannot hold more than no longer it can hold amount of water vapor. Now if you go on adding just like the salt sugar solution, you go on adding sugar to the solution, after a particular point the sugar will start to settle down. Okay, that particular point we can name it as saturation is reached. In the same way, you add some mixture to it, or you add moisture to it. In this moisture sample, you add some moisture to it, and after a particular amount of time, a particular temperature will be reached, and in this case what will happen, your moisture will be formed, and that particular temperature is called basically your wet bulb temperature. Okay. Okay, so then what we can write basically, actually how it is achieved is that, suppose this is how it is achieved, and this is basically an adiabatic container. Okay, so here, from here makeup water is passed. Okay, so from here dry air is coming and moisture is also coming. Okay, and we know that the dry air mass will remain the same, so this is the, and this is the exit uh, moisture. Okay, mv prime. Okay, so now from your energy balance we can write m dot a h a plus m dot v h b plus m dot v prime minus m dot v hw. This is for this part, because here the amount of water that will be added, that will be because of that moisture. So whatever amount, additional amount of moisture we got, this is basically the additional amount of moisture, additional amount of moisture. Okay, so this is the additional amount of moisture that actually got. Okay, so this additional amount of moisture is given by the makeup water, so that's why this is hw is the enthalpy of the water, and that will be nothing but will be equal to your outlet energy, that is m dot a ha plus m dot v prime hv. Okay, so now once again, per unit mass of dry air, this I can write this as ha plus w times hv. Okay, plus w prime minus w times hw, and that will be equal to ha plus w prime into hv. Okay, now this I can further write as w into hg minus hf plus ha plus w prime into hf is equal to ha plus w prime into hg. Okay, so this one I can write as w is equal to ha times tas, not times, it is ha at the temperature tas minus h at the temperature t. Okay, plus w prime times hg at the temperature tas minus hf at the temperature tas divided by hg at the temperature T minus hf at the temperature T. TAS. Okay, so this is an expression which we will be using to calculate specific humidity if you are provided with wet bulb temperature and dry bulb temperature together. So where it is the wet bulb temperature is basically your TAS is the wet bulb temperature and T is your dry bulb temperature. Now if you look at the psychrometric chart, okay, so what basically happens is that there are certain these types of lines. Okay, these are your constant relative humidity lines. Okay, relative humidity lines. Okay, then these lines are your let me change the color then. These lines are your specific humidity lines. Okay. And then these lines are your temperature lines. It can be wet bulb temperature, it can be dry bulb temperature, it will depend. Okay. Then okay, so then now suppose we want to locate all the points, that is all the temperatures. Okay. That is adiabatic temperature or wet bulb temperature, dry bulb temperature and dew point temperature, how it will look in a psychrometric chart. Okay, so this is your temperature T, and here either it is pressure or specific humidity, whatever you want to say. Suppose this is a particular point. Okay, this is my point 1. Okay, at a particular pressure and at a particular temperature. Okay, so from here, if I will draw a vertical line, so this is basically my T dry bulb temperature. Okay, now keeping the pressure constant, if I go on horizontally and strike at this RH equal to 100%, because if relative humidity is 100%, then it is completely saturated, strike at the 100%, so this particular temperature will be becoming my T dew point temperature. Okay, now if you want to go adiabatically, it will be a sloped line. Okay, the constant adiabatic lines are there, and if you strike at this one point, so this is basically my T wet bulb temperature. Okay, so in other case, T dry bulb temperature is greater than T wet bulb temperature, and it is also greater than T dew point temperature. Now then T okay, so these are the different things we will need to know. Now you have any doubt, you can ask, because now I will be starting the numericals. Okay. Okay, so let us start the first question then. So it is given that atmospheric air at 1.0132 bar has a dry bulb temperature of 30 degrees Celsius and a wet bulb temperature of 25 degrees Celsius. Now you are compatible with these terms, that dry bulb temperature and wet bulb temperature is what. Now from this given information, you have to calculate the partial pressure of water vapor, and you have to calculate the specific humidity of that particular mixture which it is given. You have to calculate the dew point temperature, you have to calculate the relative humidity, the degree of saturation, the density of air in the mixture, the density of vapor in the mixture, and the enthalpy of the mixture. Okay, so how will we solve then? Given P is equal to 1.0132 bar. Okay, dry bulb temperature, and that one I can write is as T dBT. T dBT is equal to 30 degrees Celsius. Okay, and T wet bulb temperature, or sometimes I can write this one as TAS, is equal to 25 degree Celsius. Okay, so now partial pressure of water vapor. Okay, so in order to calculate the partial pressure of water vapor, the formula is simple. W is equal to 0.622 times PV upon P minus PV. So from here we know only one value, that is P. We don't know what is PV. Okay, so now we have to calculate the PV part. Okay, we have to calculate the PV part. Okay, Now how will we calculate the PV part? Okay, so that means the partial pressure of water vapor. Okay, so the partial pressure of water vapor we have to calculate. So for that we need we need to calculate the partial pressure of water vapor, and for that we don't know what is W. Okay, so in order to calculate W, there is one formula. W is equals to HA at the temperature TAS minus H at the temperature T, okay, plus W prime Hg at the temperature TAS minus HF at the temperature TAS divided by Hg at the temperature T minus HF at the temperature TAS. Okay, now this numerator I can also change this upper part. I can write this one as Cp times TAS minus T. Yes or no? Because this is nothing but of the dry air. Okay, plus W prime. This one I can write this one as HFG at TAS, because Hg minus HF is nothing but HFG. Okay, and this one I can write as Hg at the temperature T minus HF at the temperature TAS. Okay, so this one we know. Now for this, these all values we will have to calculate from the stream table, but before that we will need to know what is W prime. Okay, now remember W prime is nothing but your corresponding what you call specific humidity at wet bulb temperature. Okay, so this is at the wet bulb temperature, so that means W prime is equal to 0.622 times PV at the temperature TAS divided by P minus PV at the temperature TAS. Okay, so that means PV at the temperature TAS is nothing but P saturation at 25 degrees Celsius. Yes or no? Now we need to go to the steam table. We need to go to the steam table, and we need to see the saturation temperature at 25 degrees Celsius. Okay, so saturation pressure at 25 degrees Celsius is this one. Okay, that is 0.00316999 0.0031699 megapascal. Okay, so this one I can write as 0.031699 bar. Okay, so therefore W prime will be what? 0.622 into 0.0316999 divided by 1.0132 minus 0.0316999. Okay, this is kg per kg of dry air. Okay, so quickly do this, what you will get. Zero point zero two zero kg per kg of dry air. Okay, so this is what you have got, W prime. Okay, now from steam table again, Hg at the temperature T, that is Hg at 30 degrees Celsius. Okay, so you will again go to your 30 degrees Celsius. These are your HF, HG, HFG. Okay, so Hg at 30 degrees Celsius is 2555.5. Okay, 255.5 kilojoule per kg. Okay, then HF at TAS, that is HF at 25 degrees Celsius. Okay, HF at 25 degrees Celsius, that is 104.83. 104.83 kilojoule per kg, and HFG at TAS is nothing but HFG at 25 degree Celsius. Okay, so you'll get HFG at 25 degrees Celsius is 2441.7, 2441.7 kilojoule per kg. Okay, now you put all these values. W is equal to 1.005 into 25 minus 30 plus 0.020 into 2441.7. Okay, divided by 2555.5 minus 104.83 kg per kg of dry air. Okay, so you'll get this one as 0.018 kg per kg of dry air. Okay, so this is your specific humidity of the sample. Okay, so we have got the specific humidity of the sample. Now from this we can calculate W is equal to 0.622 into PV upon P minus PV. Okay, so this is 0.018 is equal to 0.622 into PV by 1.0132 minus PV. Okay, so this means 0.018 into 1.0132 minus 0.018 PV is equal to 0.622 PV. Okay, so PV is nothing but 0.018 into 1.0132 divided by 0.018 plus 0.622 bar. Okay, 0.018 into 1.0132 divided by 0.018 plus 0.622. So this is 0.028 bar. 0.028 bar. Okay, so this is your partial pressure of water vapor of the sample. Okay, so for the sample this is the partial pressure of water vapor. Okay, now what we need to calculate? We have calculated the partial pressure, we have calculated the specific. Now we have to calculate the dew point temperature. Yes or no? Dew point temperature. Okay, so that is dew point temperature. It will be nothing but T saturation at your partial pressure water vapor. Yes or no? So that means it is nothing but T saturation at 0.028 bar. Okay, now if you look at the steam table, you will basically get this as 0.028 bar. That means 0.002 megapascal. Okay, so we have to go to the pressure table. And this is basically your value. So 22.935. So you will get this as 22.935 degree Celsius. Okay, so this is your dew point temperature. Next we have to calculate what? Relative humidity. Okay, relative humidity. Okay, so your relative humidity phi is nothing but PV divided by PVS. Yes or no? So that is PV we already know, and PVS is nothing but P saturation at 30 degrees Celsius. Yes or no? So if you go, this is your 0.028. Okay, and at 30 degrees Celsius, this is basically your 0.00424. 0.04247. Okay, so you put these values. You'll get this as 65.93%. Okay, so this is your relative humidity. Next you have to calculate the degree of saturation. Okay, so next is degree of saturation, and we have already derived the formula for degree of saturation, mu, that is nothing but phi times P minus PVS divided by P minus PV. So phi we have already got before as 0.6593. okay, 1.0132, and PVS we have got as 0.04247. okay, and this is 1.0132 minus 0.028. okay, so if you put all these values, you'll get the answer as 64.96%. okay, next you have to calculate the density of air in the mixture. okay, density of air in the mixture. okay, so that means rho A. okay, so we already know that P is equal to rho RT. so this from here rho is equals to P by RT. so therefore rho A will be nothing but PA by RA, sorry, by RA divided by TA. And so what is PA? PA is nothing but P minus PV. okay, RA we already know as 0.287 kilojoule per kg Kelvin, and TA is nothing but T dBT, that is 30 degrees Celsius. okay, so RA we will put it as, and this one. okay, so what is P? 1.0132 minus 0.028. Okay, this is in bar, so I will express in Pascal, and this will be 287 into 30 plus this will be 303. Okay, kg per meter cube. Okay, so you'll get this as 1.13 kg per meter cube. Okay, so this is of density of uh, air in the mixture. Okay, next is what? Density of vapor in the mixture. Density of vapor in the mixture. We can go by the same way also, by writing the ideal gas equation for the vapor, or what we can do is that we know W is equals to mv divided by ma. Now this one I can write as mv by v divided by ma by a, ma by v. So that means this is nothing but rho v divided by rho a. So therefore rho v is equal to W into rho a. So we already know W, that is 0.018, and we already know this one is 1.13. Okay, so this will be kg per meter cube. Okay, so this one you will get as 0.02034, 0.02034 kg per meter cube. Okay, so this is the density of vapor in the mixture. The next is enthalpy of the mixture. Enthalpy of the mixture. Okay, so that is H. Okay, so we already derived the formula for this, is that H is equal to HA plus W into HW. Yes or no? Now this HA I can write as Cp times Ta plus W into Hg. Yes or no? At the temperature T. Okay, so this is what? 1.005 into 30 plus W is 0.018 into 2555.5. Okay, that will be kilojoule per kg of dry air. Okay, so you put all this, you will get the value as 76.149 kilojoule per kg of dry air. Okay, so this is the enthalpy of the mixture. Okay, fine. So then let us go to the next question. Then now from the basics we will come to the processes. Okay, so air at 20 degrees Celsius and 40%. Okay, so you have to keep in mind that the previous question can also be solved by using psychrometric chart. So without doing that question again, you can try this at home, but I will be doing the rest of the question most either by using chart, so that you will be understanding in both the ways. Okay, so now air at 20 degrees Celsius and 40% relative humidity is mixed adiabatically with air at 40 degrees Celsius and 40% relative humidity in the ratio of 1 kg of the former and 2 kg of the latter on the dry basis. Now the final condition, you have to find the final condition, humidity and enthalpy of the air. So what is basically the condition is that there are two streams. Okay, so there are two streams of moisture. Say this is your stream 1 and this is your stream 2, and they are forming a mixture, that is 3. Okay, so you have to find W3 and you have to find H3. Okay, so given T dBT 1 is equal to 20 degrees Celsius and phi 1 is equal to 40%. Okay, and T dBT 2 is equal to 40 degrees Celsius and phi 2 is equals to your 40%. Okay, and what it is given is that m1 divided by m2 is equal to 1 by 2. Okay, this one is given. So first of all we can write mass balance. Okay, so the mass balance will be nothing but m1 plus m2 will be equal to m3. This is equation number 1. Also we can write m1 w1 plus m2 w2 will be equal to m3 w3, because the dry air concentration will not be changing. Okay, this is equation number 2. Now again the energy balance. Energy balance will be what? m1 h1 plus m2 h2 will be equal to m3 into h3. Okay, so this is your equation number 3. Now putting 1 in 2, equation 2 implies what? m1 w1 plus m2 w2, that will be equal to m1 plus m2 times w3. Okay, so this will be what? m1 into w1 minus w3, that will be equal to m2 into w3 minus w2. So from here m1 by m2 will be equal to w3 minus w2 divided by w1 minus w3. Okay, this is equation number 4. And similarly putting 1 in 3, what we get? Equation 3 implies m1 h1 plus m2 h2 will be equal to m1 plus m2 times h3, and if we do this we will get m1 by m2 will be equal to h3 minus h2 divided by h1 minus h3. This is equation number 5. Okay, so now that means what? We already have this value. Okay, we already have this value. If somehow we know w1 and w2 and h1 and h2, we get h3 and w3. Yes or no? Because we already have this ratio m1 by m2. So if we know w1 w2, we will get this, and if we know h1 and h2, and we get this. Okay, so how will we get now? So you see there is a chart given here. Okay, so in this chart you can see that the relative humidity lines are these curved lines, like this type of curved lines. Okay, these are your relative humidity lines. Okay, and that temperature lines, whatever I have shown you. Now we will be plotting the various points. Okay, we will be plotting the various points. So the first point is 20 degrees Celsius and 40% relative humidity. Okay, so we will do this 20 degrees Celsius. This is your 20 degrees Celsius, and 40% relative humidity line is this one. This is your 40% relative humidity line. So we'll go there, and this is basically the point of intersection. This one is basically your point of intersection. So from here what we will do is that we will draw a horizontal line. Okay, so this will be cutting at that particular point. So W1 is basically close to 0.006. Yes or no? W1 is close to 0.006. So this is your point number 1. Okay, and this is your W1. Okay, similarly, how can we draw the enthalpy values? So these are your constant adiabatic lines. So this is your adiabatic line. So there you will get your H value. Okay, so this is basically your H value. So this will be your H1 value. Okay, similarly My point 2 will be what? 40 degrees Celsius and 40% relative humidity. So this is again the 40% relative humidity line. So from 40 degrees Celsius will go straight until it intersects the so until it intersects the that specific humidity line 40%. So this is basically the line. So from here now, okay, and then okay, so this will basically give you H2, sorry, H2, okay. So from psychrometric chart psychrometric chart W1, okay, so W1 we get is close to 0.006 kg per kg of dry air, okay, and W2 is close to 0.019 kg per kg of dry air, okay, and similarly H1 we get close to 35 kilojoule per 35 kilojoule per kg of dry air, and H2 we get close to 81 2 3 88, okay, so 88 kilojoule per kg of dry air, okay. So therefore equation 4 now gives m1 by m2, that is half, that will be W3 minus what is W2, 0.019 divided by W1 is 0.006 minus W3, okay, so 0.006 minus W3 is equals to 2 times W3 minus 2 into 0.019, okay. So W3 is nothing but 2 into 2 into 0.019 plus 0.006 divided by 3, okay. So you'll get this one as 0.0146 kg per kg of dry air, okay. Similarly equation number 5 now implies 1 by 2, that will be equal to H3 minus what is H2, 88 divided by H1 is 35 minus H3, so this will be H3 minus 35 minus H3 will be equal to 2H3 minus 88 into 2, okay. So H3 will be equal to 88 into 2 plus 35 divided by 3 kilojoule per kg of dry air, okay. So that will be 70.33 kilojoule per kg of dry air. Okay, so we have got the enthalpy of mixture at the final state, and also we have got the enthalpy of mixture at the specific humidity of the mixture at the state at the state 3. Okay, now an air conditioning system is to take in outdoor air at 283 Kelvin, 30% relative humidity at a steady state at a steady rate of 45 per minute, and to condition it to 298 Kelvin, 60% relative humidity. So the outdoor air is first heated to 295 Kelvin in the heating section, and then it is humidified by injection of hot steam in the humidifying section. Assuming the entire process takes place at the pressure of 100 kilopascal, the rate of heat supply in the heating section, the mass flow rate of the steam required in the humidifying section. So let us first see. So it takes place in two different types of processes. Okay, so if this is basically the curve, okay, so we have to go from 1 to the point 2. Okay, from 1 to the point 2, but basically first time what happens, in the first case it is being heated to 1 to 3. Okay, and then it is being done from 1 to 3. Okay, and then from this one. Okay, so this is basically the entire process. Okay, so what it is given, T1 is equal to 283 Kelvin, so this I can write as 10 degrees Celsius, and my phi 1 is given as 30%. Okay, and T2 is given as 298 Kelvin, which I can write as 25 degrees Celsius, and my phi 2 is given as 60%. Okay, and T3 is given as 295 Kelvin, which I can write as 22 degree Celsius. Okay, so from the psychrometric chart, just like the previous question, from the psychrometric chart, what we can do, okay, we can find W1, that will be also equal to W3, because from 1 to 3 the process will remain the same, that will be 0.003 kg per kg of dry air, and W2, okay, we can write as 0.012 kg per kg of dry air. Okay, similarly we can find out H1 is equals to 16.5 kilojoule per kg of dry air, and we can find H3 is equals to 28 kilojoule per kg of dry air. Okay, now first we have to find rate of heat supplied in the heating section, that is process 1 to 3. Okay, so that means Q1 to 3, that will be equal to m dot A times H3 minus H1. Okay, so PA VA dot will be equal to MA dot RA times TA. So from here MA dot is nothing but PA VA dot divided by RA into TA. Now P is given to you as 100 kilopascal, so this will be 100 into 10 to the power 3, and it is 45 by 60 meter cube per second, and RA is 287, and TA is 283. Okay, so from here you will get this one as 0.923 kg per second. Okay, so therefore Q1 to 3 is equal to 0.923 into 28 minus 16.5 kilojoule per second it will become. So this is nothing but 10.6145 kilowatt. Okay. Next is what? mass flow rate of steam required in the humidifying section. Okay, so in the humidifying section, that means in the section 2 to 3. Okay, now change in, so for that you have to write what is the change in specific humidity. Specific humidity in the process 2 to 3, that is W3 minus W2, and W3 we have got as 0.012 and W2 we have got as 0.003 kg per kg of dry air. Okay, so this is basically your 0.009 kg per kg of dry air. Okay, so this is the change of humidity. Now this change in humidity is basically provided by your steam flow, yes or no? So this will give us the mass of this mass flow rate of the steam flow. So that means what? This is per kg of the dry air. Now if we multiply by the mass flow rate of the dry air, then we will get the mass flow rate of the steam. So therefore mass flow rate of steam required in the humidifier is equal to what? Ma dot into W3 minus W2. What is Ma dot? 0.923 and W3 minus W2 is 0.009. So this will be kg per second. Okay, zero point 0.0083 kg per second. Okay. So let us go to the next question. What is the lowest temperature that an air can attain in an evaporative cooler if it enters at 1 atmosphere and 302 Kelvin and 40% relative humidity? Okay, so what is the lowest temperature that it can attain? Okay, so we all know that the lowest temperature is nothing but the dew point temperature. There are three types of temperature. One is the dry bulb temperature, one is the wet bulb temperature, and another one is the dew point temperature. So basically it is trying to tell us that find the dew point temperature at this particular given conditions. Okay, so what we are telling us, P is equals to 1 bar. Okay, T is equal to 302 Kelvin, and this I can write as 302 minus 273 degrees Celsius, which will be equal to 29 degrees Celsius, and phi is given to US 40%. Okay, so we know phi is equal to PV by PVS. Okay, now PVS we can write this one as from the steam table at 29 degrees Celsius. So this we will get as 0.0040092 megapascal. Okay, so therefore PV is equal to 0.40 into 0.004092 megapascal. Okay, so this will be 0.00160,368 megapascal. Okay, so this is my PV. So now therefore at this particular PV, from the steam table I can find the dew point temperature. So therefore the lowest temperature attainable at the evaporative cooler is equal to what? T saturation at P equals to PV. Okay, so that means T saturation at 0.00160 368 megapascal. Okay, and if you go to the steam table, you will get this one as 14.010 degrees Celsius. Okay. Fine. So let us go to the next question then. Consider a room that contains air at 1 atmosphere, 308 Kelvin, and 40% relative humidity. Determine the specific humidity, enthalpy, wet bulb temperature, dew point temperature, and specific volume of the air. So just like the question number 1, this question we will be solving also, finding the properties at a particular given thing. But here what we will do, we will use the psychrometric chart to solve this particular problem. Okay. So given P is equal to 1 atmosphere, T is equal to 308 Kelvin, which is equal to 35 degrees Celsius, and phi is equal to 40%. Okay, so determine the specific humidity. Okay, number 1, specific humidity. Okay, so that is W. So how will we find? Once again, this is my 40% relative humidity curve. Okay, and 35 degrees Celsius is 35 degrees Celsius is this one. So from here I will go to here. Okay, so this is my point of intersection, this is basically my point. So from here I will draw this horizontal line. So this is 1. So W is equal to 0.014 kg per kg of dry air. Okay, next, enthalpy, that is H. Okay, so from this line I will draw an inclined line to this point. Okay, and this is basically your this point. Okay, so enthalpy H is equals to 70 kilojoule per kg of dry air. Okay, next is wet bulb temperature. Okay, so for wet bulb temperature, what we will do, we will go to here, and from here we will draw a vertical line, and this is something 21, 22, 23. Okay, so you can write this as TWBT is equal to 23.5 degree Celsius. Okay, so that is your wet bulb temperature. Then next, dew point temperature. Dew point temperature. Okay, so for dew point temperature, this line you go straight here, and from here you draw this vertical line, you'll get almost 19 degrees Celsius. Okay, so this is T dew point temperature is equal to 19 degree Celsius. Okay, so you have got dew point temperature. Now you need to know the specific volume. Okay, so the specific volume lines are these lines. Okay, so this line is 0.89, so 0.89 something like that. Okay, so this will be close to specific volume will be 0.89 meter cube per kg. Okay, so very simple question. Just in the question number 1 we were solving it by solving some equations analytically, and but in this case what we have done is that we have solved it by using the psychrometric chart. Okay, next is what, 30 per minute of moisture at 15 degrees Celsius dry bulb temperature and 13 degrees Celsius wet bulb are mixed with 12 per minute of moisture at 25 degrees Celsius dry bulb temperature and 18 degrees Celsius wet bulb temperature. Determine the dry bulb temperature and wet bulb temperature of the mixture assuming barometric pressure as 1 atmosphere. Okay, this is the same, but in this case now instead of giving the temperature directly, they are giving that both the dry bulb temperature and wet bulb temperature. So then how you will calculate the dry bulb temperature and wet bulb temperature of the mixture that is formed. Okay, so like this, adiabatically two streams are mixed. Okay, say this is 3, this is 1, and this is 2. Okay, so what it is given to us, v1 dot is equals to 30 per minute, which we can write as 30 by 60 meter cube per second. Okay, T dry bulb temperature 1 is equal to 15 degrees Celsius, and T wet bulb temperature 1 is equal to 13 degrees Celsius. Okay, similarly V2 dot is given to you as 12 per minute, which I can write as 12 by 60 meter cube per minute, and T dry bulb temperature 2 is equal to 25 degrees Celsius, and T wet bulb temperature 2 is equal to 18 degrees Celsius. Okay, now how will you find given your dry bulb temperature and wet bulb temperature? Okay, now see, at the wet bulb temperature the thing is already saturated. Okay, so we will first locate the 13 degrees Celsius where it cuts the relative humidity 100%. Okay, so the 13 degrees Celsius, this is 1, this is 1 2 3 4 5. Okay, so 1 2 3, 13 degrees Celsius line, this is somewhere, this is the 13 degrees Celsius. Now from here we can draw an inclined line up to 15 degrees Celsius. Okay, so this is basically your point number 1. Okay, so this is your point number 1. Similarly 18 degrees Celsius with this is your 18 degrees Celsius. Okay, and from 18 degrees Celsius you will draw to mix that 25 degrees Celsius. So this will be your point number 2. Okay, so this is the line. Okay, now from here what we can get, W1 and W2. Okay, so W1 is equal to 0.007 kg per kg of dry air, and W2 is equal to your 0.010 kg per kg of dry air. Okay, and specific volume V1, this is your 0.080, 0.001, 0.082. Okay, so 0.82 meter cube per kg, and V2 is your almost close to 0.86 meter cube per kg. Okay, so conservation of mass or mass balance what we can write the mass balance as m1 dot plus m2 dot will be equal to m3 dot. Okay, and again m1 dot w1 plus m2 dot w2 will be equal to m3 dot w3. Now this I can write again, m1 dot w1 plus m2 dot w2 will be equal to m1 dot plus m2 dot times w3. Now m1 dot times w1 minus w3 will be equal to m2 dot times w3 minus w2. Okay, so from here m1 dot by m2 dot will be equal to w3 minus w2 divided by w1 minus w3. Okay, this is my equation number 1. Okay, now m1 dot, I can calculate this one as v1 dot divided by v1. Okay, so v1 dot is 30 by 60 and v1 is 0.82. If you put all this, you'll get this one as 0.609 kg per second. Similarly, m2 dot will be nothing but v2 dot divided by v2. Okay, so v2 dot is 12 by 60 divided by 0.86, and if you put this, you will get this one as 0.232 kg per second. Okay, so therefore equation 1 now implies what? 0.609 divided by 0.232 is equal to W3 minus 0.010 divided by 0.007 minus W3. So if you solve this, you will get W3 approximately equal to 0.008 kg, not get 0.008, I'm sorry. Yes, you'll get somewhere W3. Solve this, what you will get? 0.609 into 0.007 minus 0.609 W3 will be equal to 0.232 W3 minus 0.010 into 0.232. Okay, so that therefore W3 will be equal to 0.609 into 0.007 plus 0.010 into 0.232 divided by 0.609 plus 0.232. Okay, kg per kg of dryer. Okay. 0.609, 0.007 plus 0.010 into 0.232 divided by 0.609 plus 0.232. So you will get this approximately equal to 0.0078 kg per kg of dryer, which I can approximately write as 0.008 kg per kg of dryer. Okay, so now since intermixtion or what you call, this is a linear process, so from 008 we will draw a straight line, okay, which will intersect here. So this will be basically my dry bulb temperature, that is 1 2 3 4 5 6 6. Okay, so my T dry bulb temperature of the mixture is equal to 16 degrees Celsius, and T wet bulb temperature of the mixture, that will be equal to, so from here you go there, then you do this, so it will get almost 13.2 degree Celsius. Okay. Fine. So let us come to the last question then. Okay, so water enters a cooling tower at 38 degrees Celsius with a flow rate of 50 into 10 to the power 6 kg per hour from the condenser of a power plant. The stream of the cooled water is returned to the condenser at 30 degrees Celsius with a flow rate, with the same flow rate. Makeup water is added to the cooling tower at a separate stream at 20 degrees Celsius. and then atmospheric air enters the cooling tower at 25 degrees Celsius, 35% relative humidity, and the moisture leaves at 35 degrees Celsius and 90% relative humidity. Determine the mass flow rate of the air, mass flow rate of the makeup water, and approach and the range of the cooling water. Okay, so let us first draw the schematic diagram of this cooling tower. Okay, so atmospheric air in atmospheric air in and moist air out. Okay, now this is somewhat liquid water that is coming from the power plant, liquid water in. Okay, and this is somewhere liquid water out. Okay, and then it is going back to the power plant. Okay, so that means it is required to cool down. Okay, now in doing so there will be some condensation or evaporation process for that. If the water gets lost, so there will be some makeup water will be added from here. Okay, makeup water. Okay, now if we name this as point 1, we name this as point 2. Okay, you name this as point 3, this is also a point 3, and we name this as point 4. Okay, so what are the things that are given to us? M1 dot is equal to 50 into 10 to the power 6 kg per hour. Okay, T1 is given to us as 38 degrees Celsius, and M2 dot is nothing but M1 dot. Okay, and T2 is given to us as 30 degrees Celsius. Then M dot 5 we don't know. Okay, if this is the point number 5. Okay, and T5, that is the makeup water, is given to you as 20 degrees Celsius. Then T3, that is entry air, is given to you as 25 degrees Celsius, and phi 3 is given to you as 35%. Okay, similarly outgoing is T4 is given to you as 35 degrees Celsius, and phi 4 is given to you as 90%. Okay, fine. So now from steam table, state 1, okay, that is water at 38 degrees Celsius, HF1 is equal to 159.2 kilojoule per kg, and state 2, okay, that is water at 30 degrees Celsius, so you'll get HF2 is equal to 125.79 kilojoule per kg. Okay, then state 5, that is at 20 degrees Celsius, or is it state 5? Yes, 20 degrees Celsius. HF5 is equal to 83.96 kilojoule per kg. Okay, next state 3, 25 degrees Celsius, Hg3 is equal to 2547.2 kilojoule per kg. Okay, and state 4, that is 35 degrees Celsius, Hg4 is equal to 2565.3 kilojoule per kg. Okay, so again from psychrometric chart, what we can find, TWBT3 is equal to 16 degrees Celsius and W3 is equal to 0.007 kg per kg of drive. Okay, and W4 I can find as 0.03 kg per kg of drive. Okay, so now ma dot, okay, so that means what, mass flow rate of the air, mass flow rate of air. Okay, so ma dot is equal to what, m1 dot hf1 minus hf2 divided by ha4 minus ha3 plus w4 into hg4 minus w3 into hg3 minus w4 minus w3 into hf5. Okay, so if you put all these values, what you will get, 50 into 10 to the power 6, 159.21 minus 125.79 divided by 1.005 times 35 minus 25 plus 0.03 into 2565.3 minus 0.007 into 2547.2 minus 0.003, sorry, minus 0.03 minus 0.007 into 83.96. Okay, you put all these values, you will get ma dot is equal to 2.4 into 10 to the power 6 kg per hour. Okay, therefore m5 dot is equals to what, 2.4 into 10 to the power 6 into 0.03 minus 0.007, because this is basically what, ma dot into w4 minus w3. Okay, so therefore this you will get as 5.5 into 10 to the power 5 kg per hour. Okay, so this is your mass flow rate of makeup water. Okay, now next is what, approach and range of cooling tower. Okay, so approach is equal to what? T1 minus T wet bulb temperature at the point 3. Okay, so T1 is 38 degrees Celsius and wet bulb temperature is at 16 degrees Celsius. So this is equal to 22 degrees Celsius. And what is range? Range is nothing but T1 minus T2, and T1 is 38 minus 30, that is 8 degree Celsius. Okay, so I have concluded today's class. If you have any doubt, you can ask me. I stop for today. Thank you very much for listening.